Hi there. I hope you're looking forward to this lesson. It's really been a joy to teach in my classroom, and I hope it's a joy to teach in yours as well. I have lots of things that I want to tell you, so please pardon my notes as we go along. So this lesson on fractals was designed for students who have a mastery of basic algebra skills. So in the United States, that often means maybe a 10th grade or 11th grade level, and that's the level that I've taught it at in the past. It also requires a knowledge of complex arithmetic, which is not a topic that gets taught in all of the algebra classes. So to achieve that topic and to prepare the students for the lesson, we've actually written a tutorial on complex arithmetic. And this tutorial can be used in a number of ways if your curriculum doesn't cover complex numbers. One way to do it is to assign it to your students as homework the night before you do the lesson. It's designed to start from the basics, from a student who knows algebra but knows nothing about complex numbers, and bring them up to the level where they can add, subtract, multiply, and take the absolute value of complex numbers. So it walks them through these steps, and it gives them some practice with it. Alternately, you could decide to actually work through the tutorial in your classroom. So take the day or a few days before you decide to do the fractals lesson, and give your students time in a group and with you to get comfortable with the mechanics of complex arithmetic before you launch into this material. We've also included in the written material that goes along with this lecture a very quick quiz on complex arithmetic. And depending on your class, maybe you want to use it the morning that you do this lecture or assign it in advance, just to check the comprehension of the students before you, again, launch into the more complicated material. So that being said, the actual mechanics of the math that's in this lesson are not too hard. They're addition, subtraction, multiplication of numbers. What's difficult about the lesson is that it introduces some really sophisticated new concepts for students that require kind of a lot of mathematical maturity. Difference equations, initial conditions, trajectories, boundedness. These are all really quite sophisticated ideas. So you're going to play a really important role in helping your students understand and feel comfortable and develop intuition about these new topics. So I hope you're up for the challenge. Okay, so let's get started. So part one of the lecture is an experiment called the chaos game. Now, in the video, I present it and suggest to the students that they pursue it as a thought experiment. So the way I've done it in my classroom in the past is broken the students up into pairs and had them work together and just brainstorm what they think the final pattern of dots is going to look like. Often it helps to hand each pair of students a piece of paper with an equilateral triangle already drawn on it, and that way they can kind of plot out some points and look at it and do some discussing. Alternately, you might want to try actually running this experiment in your classroom. And Robert Devaney is an educator who suggested one way to do this is to hand small groups of students or individual students an overhead transparency sheet, so a clear sheet of paper. You also hand them a permanent marker and then some kind of die or a way for them to run the experiment. So some way of selecting red, green, and blue or three equally likely things. So if you had a die, you could use a die. You could make your own like the one I used in the video. If you wanted to, you could draw 3 different colored marbles out of a bag or out of a hat. Any of these ways would work just fine. So if you hand each of your students this overhead transparency sheet with a triangle drawn on it, and have them actually run this experiment and draw dots on the overhead sheet. Robert Devaney suggests that when you're finished with this process, you can take all of the transparency sheets and stack them up and then project through them onto the wall. And the idea is that this is a very quick way of generating a whole lot of points, and you should be able to get a sense of what the final pattern looks like. I think in order to make this successful, you'd have to have some really, really precise students, because when I tried this with a group of teachers in the past, the result was a completely incoherent mess. We couldn't see any patterns at all. So I recommend doing some experimenting with this before you get started, before you bring it into your classroom. An alternate way of doing it would be to actually write a computer program that would do it. And actually, at the end of this lesson, in the very final section, we present the results of a computer simulation that's playing this game. If you have students in your class who are taking a computer programming class, or who know something about computer science, this might be a fun project for them to do. Have them write a little piece of software that will do this, play this game for the whole class. It could be a really interesting extension. Okay. Speaking of extensions, you may get questions on extensions. So, for example, what happens if you don't start the game at one of the vertices, but you start at some point in the middle of the triangle? Are you still going to get the same kinds of patterns? These questions are what makes it a lot of fun to be a teacher. So the more thinking you can do about the kinds of questions your class is likely to ask and the answers to them, or at least giving them pointers to where they can explore the answers to the questions themselves, that could be really great. And the written material that accompanies this video lecture includes a lot of possible extensions. So I hope you'll take a look through those and maybe get some of your more excited students to pursue some of those topics. Okay, so that's part one, playing the chaos game. Part two is the introduction to difference equations. Now, right away, some of your students may have trouble with this because a difference equation is very different than the kinds of equations they're probably used to seeing. In a lot of ways, it's more like a rule and kind of a formal equation that they're going to have to solve. We start to try to develop students' kind of comfortability with this idea of difference equations by talking about the Fibonacci sequence. Often in my classroom, there's been one or two students who have seen it somewhere else in their previous math background, but many students haven't. It's a really great topic, just the Fibonacci numbers themselves, for high school algebra and geometry classes, because there's a very strong geometric component to the Fibonacci numbers. They have a lot of interesting applications, and there's a lot of interesting and not too complicated mathematics that can really give high school students a glimpse into what mathematics at the college level might be like without bogging them down in too much material that they don't have the background for. So I highly recommend encouraging your students to pursue different areas of applications of the Fibonacci numbers. And again, there are some discussions of that material in the written material that accompanies this lecture. So as I said, this section introduces difference equations and initial conditions. Really, what's needed more than anything here is just time and practice. Students need to get familiar with looking at a difference equation, being comfortable computing a trajectory, and experimenting with what happens with different initial conditions. A really useful format that you can apply to the problem solving that happens throughout this entire lecture is to break the students into small groups, present them with the examples that we discuss or that we present in the video, have them work in these small groups for a little while, and then bring the entire class back together and assemble all of their results so that everybody can see them. So if you can put them all up on the board, that's a really useful thing. And that's especially useful when you're talking about difference equations and calculating example trajectories, because then you can get a lot of different kinds of trajectories without having every student have to go through all of the different possibilities. Okay, so part three, we introduce the idea of boundedness. And I think this is one of the more sophisticated ideas that gets introduced in this lecture. And I think you'll probably end up spending a lot of time helping students develop intuition on the idea of boundedness. So often I find it helpful to phrase kind of boundedness in the following way. If a trajectory is unbounded, then it's not possible to find any single number such that the absolute value of the trajectory is always less than that number. So if you can find such a number, even if it's a really big number, even if it's 100 million, if you can find a number such that the absolute value of the trajectory is always less than that number, then it's bounded. And you'll come up with all sorts of different ways of explaining what a bounded trajectory is versus an unbounded trajectory. A useful tool to use in the classroom is to encourage your students to challenge each other. So present a difference equation and an initial condition. Look at what the trajectory, calculate a few points of it, and then ask the class, is this bounded or unbounded? Often they'll have an intuitive answer. Well, it looks like it's blowing up, or it looks like it's not. But see if you can get them to use the mathematical language. Ask them to prove it to you. Find me, if you argue that it's bounded, find me a number that the absolute value is always smaller than. If you argue that it's unbounded, tell me why. Another issue that often confuses students is when a trajectory is bounded, a number that serves as a bound for that trajectory is not unique. So, for example, if the absolute value of a trajectory is always less than 2, well, then the absolute value is always less than 3 as well. So students often find it difficult to kind of handle this non-uniqueness in terms of boundedness. So that's something you may have to discuss explicitly in your class. Okay, in part 4, we add a twist to the material we've done so far. We allow our difference equations to take on complex values. So maybe we give them complex initial conditions, or the difference equations themselves have a complex number in them. None of the mechanics are any different, but it requires them to use complex arithmetic. And depending on how comfortable your students are with complex arithmetic, this can be more or less difficult. This is another one of those topics that will just require time and practice. So having extra examples and allowing enough time for students to work through those examples will be really important to helping them feel comfortable with the idea of complex trajectories. Now, in order to evaluate whether or not a complex trajectory is bounded, students need to be able to take the absolute value of a complex number. And this is a topic that is addressed in the tutorial, but if you discuss complex arithmetic in your class outside of the tutorial, make sure that students know how to find the absolute value of a complex number in order for them to be able to work through this section. So part 5 introduces the Mandelbrot set. And in some ways, this is conceptually the most lovely part of this entire lecture. At this point, students need to feel comfortable with deciding whether or not a trajectory, a complex one, is bounded or unbounded, because that's the way you define what points are in the Mandelbrot set or not. But hopefully, by this point, all of the hard work and heavy lifting has been done by your students in terms of the mechanics and kind of intuition building on trajectories. And they can kind of just enjoy the beautiful results that come out. So at the end of this section, we ask the students to guess what the Mandelbrot set is going to look like. And this is one of those times where you don't need to spend too much time in class on having students brainstorm and then coming back together with a suggestion. Because the answer is so strange and seemingly unpredictable that it's really more a thought exercise at this point, and they're kind of waiting to see what the final answer is going to be. So the very last section is on fractals in general. And it really is just a very brief introduction to some beautiful images that will hopefully inspire your students to pursue some of the extensions that we were talking about earlier and to do future work in this field. At the very end, we also return to the chaos game and the Sierpinski triangle. And as I mentioned earlier, we present the brief computer simulation that shows you kind of the very surprising and interesting pattern that the chaos game will result in. And so I hope by the end of this lesson, your class has learned an extraordinary amount of new material, most material that students in high school never get a chance to see, and that all of you have kind of become interested in a brand new topic that could take you in all sorts of directions in algebra and geometry and beyond. So thank you very much for your interest in this lesson. I really hope you enjoy making this lesson on fractals exciting and interesting to your class, and I wish you the best of luck.